Okay, this is the test review for exam 1. Question 1. This comes from section 2.1. You're supposed to evaluate a piecewise function. Key thing is that this is a function, so for every input you can only have one output. So the first one here, f of 8, can only have one answer. You cannot plug 8 into both pieces, otherwise you're going to get two different outputs. So 8 fits into this piece of the domain, x is greater than 6, so you need to plug 8 into that piece of the function. 2 times 8 equals 16. The next one, f of negative 1 fits into this part of the domain when x is less than or equal to 6, so you have to plug in a negative 1 into that piece of the function. So negative 1 squared plus 6 times negative 1 is equal to 1 plus negative 6, which is negative 5. And finally, f of 6 still fits into this piece, x is less than or equal to 6, so you need to plug 6 into that piece. So that's 6 squared plus 6 times 6, that's 36 plus 36, which is 72. Question 2, evaluate the difference quotient. The way that this was presented in class is to break this down into different pieces. F of A, F of A plus H. So F of A, you simply place an A into the function for all the x's, so that becomes 4a squared plus 1. F of A plus H means that wherever there was an x in the original function, there used to be an x right here, but I replaced it with an empty parenthesis. Wherever the parentheses are, that's where you place the input a plus h. A plus h to the second power is a squared plus 2ah plus h squared. Distribute the 4. So putting this all together now, using this as a pattern, f of a plus h, which is this, and then you subtract f of a, so subtract 4a squared plus 1 all over h. Now at this point, excuse me, a lot of terms in the numerator should cancel. The 4a squared, negative 4a squared, positive 1, that really is a negative 1 if you were to distribute that minus sign. So you have 8ah plus 4h squared all over h. The numerators, if you look at the numerator, you can factor out an h from each term. And you can cancel the h that you factored out with the h in the denominator. So the answer is 8a plus 4h. Question 3, find the domain. This is still from section 2.1. The domain of a square root, or if this were a 4th root or a 6th root, any kind of even root, the way that you find the domain is you take the expression inside the root, in this case 6 minus 2x, and you set it greater than or equal to 0, and then solve the inequality. Remember, when you divide by negative 2 on both sides, you switch the direction of the inequality, and you get x is less than or equal to 3, so the domain is negative infinity to 3. Question 4, the domain of a rational function, a function that's in the form of a fraction. Make sure it's in factored form. It's okay for the numerator to equal 0. That's not a problem. The problem is going to be in the denominator. You can't have a 0 in the denominator, so x cannot equal plus or minus. 2. So the domain in interval notation is from negative infinity to negative 2, and then from negative 2 to positive 2, and then from 2 to infinity. Question 5, again, look at it in factored form. Now we do have to consider the numerator. The numerator can equal 0, but you have a square root. So we need to consider that x has to be greater than or equal to 0. Otherwise it can't be inside of a square root. The other thing to consider is here in the denominator, x cannot equal 11 and x cannot equal 5. So all of this needs to be put together into an interval. X has to be greater than or equal to 0, and it can't equal 11 or 5. So starting at 0, including 0, that's why it's a bracket, 0 to 5, and then from 5 to 11, and then from 11 to infinity. Question 6. Determine whether this equation is a function of x. That means if you plug in one number for x, you should get one number out for y. One way to do that is to try to rearrange the equation into a y equals equation. So for this one, if you subtract the x squared, you're going to get 3y equals negative x squared plus 3, and then if you divide by 3, you're going to get y equals negative x squared over 3 plus 1. Now you've got to decide whether or not this is a function of x. Like I mentioned earlier, you can plug different numbers in for x to make sure that you only get one number out for y. Perhaps an easier way for this problem is to imagine or to try to graph this. If it's an x squared, it's going to be a parabola. Because it's a negative in front, it's a parabola that's facing upside down, and it's moved up 1 unit. So just a quick sketch of the parabola may look something like that. It's a function because it passes the vertical line test. Another way, you could just make a table of values and plug in different x values. Make sure you only get one value out for y, but this is the equation of a function. Specifically a function of x. Now question 7, if we move the absolute value of y to the other side, we're going to have the absolute value of y is equal to 5x. Now this is kind of digging into your knowledge of absolute values from 1010 or from Math 990. But one way to solve an absolute value equation is the expression inside the absolute value is equal to 5x, and then you have to make the expression inside the absolute value its opposite, so negative y also equals 5x. So this statement implies that 5x is equal to plus or minus y. Now this is a problem. If I plug in a number for x, 2 for example, so if I make a table of values, if I plug in a number for the number 2 for x, 2 times 5 is 10. 10 is equal to plus or minus y, so plus or minus 10. So I plugged in one number for x, I got out two different numbers for y. This would not be the equation of a function. So, question 8, find f of negative 1. Typically you would have an equation to plug the negative 1 into. but we don't have the equation, we have the graph. So -1 is an x value. If you find the x value here on the x-axis, then the answer would be the corresponding value on the function, -1, 3. So f of -1 is equal to 3. State the domain and range. The graph didn't come over quite as I had hoped. There's supposed to be an arrow there and an arrow there. That implies that the graph continues upward and downward in both directions. So the domain, if we were to choose any value along the x-axis, eventually we could find a point on the graph with that x value. No matter how far in the negative direction, no matter how far in the positive direction, any number on the x-axis is going to have a point on the graph somewhere. So the domain is all real numbers. Similarly for the y-axis, any number I choose on the y-axis, no matter how high or how low on the y-axis, is going to have a point corresponding to it on the graph. So the range is also all real numbers. State the intervals in which the function is increasing and decreasing. You read a graph from left to right, so starting here, if we're reading the graph from left to right, all of the points, if we're going from left to right, the points are increasing, or the y values are increasing. So this interval right here would be an increasing interval on the graph. And the way that this is stated is all of the x values on which this is occurring. So all of these x values here, the graph is increasing. And then the graph starts to decrease. So between these x values right here, the graph is decreasing, and then it begins to increase again. So starting here and all the way there. So these intervals that I've highlighted in black on the x-axis, these are intervals where the graph is increasing. So increase from -infinity to -1. It's also increasing from 1 to infinity. Decreasing interval would be between -1 and +1. Is the function even, odd, or neither? Graphically, the way that you can spot a function that's even or odd or neither, even functions, an even function is the same on the y-axis, on both sides of the y-axis. It would be symmetric about the y-axis. This graph is not symmetric about the y-axis, so it's not even. An odd function has the symmetry of being symmetric about the origin. So on a graph here, one way to spot symmetry about the origin or an odd function would be this property here. This is the point 1, -3. So if this were an odd function, then it would have the point -1, +3. You change the sign of both x and y. And if we check that up here, we've got a point of -1, +3, and that should be true of every point. Like this one here is a point +2, 0. So over here, it's opposite, -2, 0 is also on the graph. That's an indication that this is an odd function. Local extrema, remember that means the local max or maximums if there are more than one, and the local minimums. So local max is the highest point in a very small region of the graph, this region of the graph, for example. That point right there is the highest point in that region of the graph. It also happens to be when the graph switches from increasing to decreasing. So there's a local max at the point -1, 3. Local min, if we consider that region of the graph, and just that small region, that's the lowest point in that region, so that would be a local minimum that occurs at the point 1, -3. Is the function one-to-one? A one-to-one function passes a horizontal line test. It's obviously a function because it passes the vertical line test, but if I were to draw a horizontal line anywhere through the graph, it hits, in this case, 3 times, so it fails a horizontal line test, so it is not 1, 2, 1. It fails the horizontal line test. Okay, the average rate of change. Average rate of change is really just the slope of a line between a line connecting 2 points on this graph. So this is the graph of a parabola. You know, it would look something like this. And then we would have 2 points on the parabola. You know, maybe here and here. If we connected those 2 points like that, the slope of those 2 points would be the average rate of change. Now this can be done graphically or algebraically. More precise way would be algebraically, and it's just a slope function, f of x2 minus f of x1 all over x2 minus x1, where this could be x1 and that could be x2. So f of x2 is equal to negative 2 squared minus 9 times negative 2. F of x1 is equal to negative 3 squared minus 9 times negative 3. So here we get 4 plus 18, and here we get 9 plus 27. So f of x2 minus f of x1 is going to be 22 minus 36 all over x2 minus x1, so that's negative 2 minus negative 3. This becomes negative 14 all over 1, which equals negative 14. So this is another average rate of change. Again, remember, or try to remember, average rate of change is just the slope of a line that connects 2 points on a graph. So between x equals 0, which is right here, and x equals 100, which is right there, you would need to find the slope of the line that connects those 2 points. So we could do this like we did the last problem algebraically. We could say this is x1 and that's x2, so we need to find f of x2 minus f of x1 all over x2 minus x1. Well, f of x2 is just f of 100. Now if we go over to 100 on the x-axis and go up to the graph, it looks like it's 75, so f of 100 is equal to 75. Now, f of x1 remember is 0, so if we go to 0 on the graph, it's at 50, so f of 0, or f of x1, is equal to 50. x2 minus x1 is 100 minus 0, so that's 100. You get 25 over 100, which is 1/4. So looking at the graph, if we try to see the reasonableness of our answer, the slope of this line, if we go up 25 and over 100, remember slope is rise over run, so we go up 25 over 100, so that's the correct slope, but this represents actual data, so we perhaps should be a little more specific here. 1/4, 1 over 4, what do those values represent? 1 represents a quantity and 4 represents a quantity. So remember the slope is rise over run, so this is the vertical direction. The y-axis here represents the depth of water, and the x-axis represents days. So it doesn't give The depth doesn't say whether it's in feet or what. So this question needs to be asked a little more specifically. It should be 1 foot per 4 days. Okay, this transformation here describes a horizontal reflection. Had the minus sign been outside of the function, that would have been a vertical reflection. There's two transformations here. There's that and that. Since the minus 3 occurs outside of the function, it affects vertically. It affects the graph vertically. It moves the graph down 3 units. The 7 is also outside of the function, so it affects the graph vertically as well. But since it's multiplying, it stretches vertically by a factor of 7. So we have the same transformation here. Moves down 3 units. Then we have this transformation, moves left. Remember, if it's inside of the function and it's adding or subtracting inside the function, it moves left to right, and inside the function is opposite. So plus 5 actually moves left 5 units. And then we have that transformation there, similar to this transformation. It stretches vertically by a factor of 4. Okay, for a problem like this, I would recommend identifying key points on the graph. -5, 0, 0, 5, 2, 1, and 5, 2. And then making a new table of values for each different type of transformation. So this one, for example, 1/2 of f of x. The 1/2 is outside of the function, so it's going to affect the y column or the y values. 1/2 of f of x means 1/2 of the y values. So making a new table of values, the x column stays the same because this transformation has only affected y values. The y values are going to change by a factor of 1/2. So half of 5 is 2.5. Half of 1 is 0.5. Half of 2 is 1. So this is a vertical shrink or compression compared to the original function. It has the same horizontal width, but in the vertical direction it's been compressed. Now this one here, f of 2x, since it's inside the function, it's going to affect the x values, but it has the opposite effect. Rather than multiplying the x values by 2, they're going to be divided by 2. Inside the function is opposite. So, referring back to the original table, the y values this time are not going to change. It's the x column that changes, and you have to remember inside the function is opposite. Rather than multiplying the x values by 2, they are cut in half. So the graph has the same vertical component, so it's the same height, it's just the width has changed. Okay, question 18. This is the original function f of x equals x squared. We need to come up with an equation for this graph here. It's moved 4 to the right, up 2, and it's reflected. So 4 to the right means x minus 4 inside of the parenthesis. Up 2 means a plus 2 outside of the parenthesis, and reflected vertically means a minus sign out in front or outside of the function. So there's the equation or a formula for the g function. Okay, we need to find g of f of 5. But let's break this apart. First of all, what is f of 5? Well, f of 5, since this right here represents the f function, if we go out to 1, 2, 3, 4, 5, right here, one, two, three. So f of 5 is equal to 4. So now I'm going to make the substitution. If f of 5 is the same thing as 4, I'm going to place that 4 right up in there and find g of 4. So now on the g function, 1, 2, 3, this is 4. On the g function, it's not super clear, but the graph does continue to go all the way down to that point. So 4, comma 3. So g of 4 is equal to 3. So the original g of f of 5 is equal to 3. Okay, we have a $50 coupon, but it's also offering a 20% discount on cell phones. And X represents the regular price of the cell phone. So this actually does happen, and it depends on how the discounts are applied, whether or not you get a good deal or a deal that's in the store's favor. And that's the point of this problem. So suppose only the 20% discount applies. Find a function f that models the purchase price as a function of x or the regular price. So if you're getting 20% taken off, that means you're only paying 80% of the original purchase price. So the function f is 80% of the purchase price. That's what you're paying because you're getting 20% off. Now for part B, the g function is $50 off. So if the original price is x, you take off 50. That's what you would pay if you're only using the $50 coupon. Now, if you can use the coupon and the discount, then the purchase price is either the composition f of g of x or g of f of x, depending on the order that they are applied. So f of g of x is the g function here going in place of the f function. So this would be 0.80, and then instead of x, I'm going to make an empty parenthesis, and that's replaced with x minus 50, so that's 0.80 x minus 40. So you pay 80% of the purchase price, and then you take $40 off of that. That's what f of g of x is saying. G of f of x, now the f function is going inside of the g function. So the g function has x minus 50, so that's parenthesis minus 50. And then the parenthesis gets filled in with the f function, which is 0.80 x, and that equals 0.80 x minus 50. So this one you get 80%, you pay 80% of the purchase price, and then you subtract $50. So you both compositions have the customer paying 80% of the purchase price, but g of f of x, you're subtracting more off at the end, $50 off rather than $40 off. So this is the better deal. So the way that this needs to be applied, if you start on the inside, the f function has to happen first. That's 20% discount, and then subtract $50. So 20% discount applied first, then take off the $50. Okay, adding these two functions, they can only be added if they have a common denominator, so this side needs to be multiplied by x minus 4 over x minus 4. This side needs to be multiplied by x minus 2 over x minus 2. Now, here in the numerator, we're going to get 3x minus 12. Here, if we multiplied those together, we would get x squared minus x minus 2. Now that they have the same denominator, they can be added together by collecting the like terms in the numerator. The denominator stays the same, x minus 4 over x minus 2. If we combine like terms in the numerator, we're going to have x squared plus 2x minus 14. It also says state the domain of each. In f plus g of x, x cannot equal 4, x cannot equal 2, otherwise we'd be dividing by zeros in the denominator. So the domain is from negative infinity to 2, 2 to 4, and 4 to infinity. Now for part B, we were just about there in part A. All we'd have to imagine now is the plus sign being replaced by a minus sign, so we'd have 3x minus 12 over x minus 4, x minus 2, minus x squared minus x minus 2 over x minus 4, x minus 2. Now collecting the like terms, remember this minus sign has to distribute to the numerator there, so we're going to have negative x squared. This minus x is really a plus x now, because a negative times a negative is a positive, so we have an x plus 3x, which is 4x, and a negative times negative 2 is a positive 2, so negative 12 plus 2 is negative 10, and it's the same domain. X cannot be 4, x cannot be 2. Now for f multiplied by g, you don't have to have the same denominator. So going back to the original functions, 3 over x minus 2 multiplied by x plus 1 over x minus 4, all you got to do is multiply straight across. So if the 3 multiplies there, you're going to get 3x plus 3 over x minus 2 times x minus 4. Same domain, x cannot be 2 and x cannot be 4. Now for part D, dividing two fractions is the same as multiplying by the reciprocal of the second fraction. So we're going to get 3x minus 12 if you distribute the 3 in the numerator over x minus 2, x plus 1. So now we have something new to consider. X cannot be 2, x cannot be negative 1. But we also have to consider the original problem. This answer is only possible because we're claiming that this is possible, and this can only be possible if x does not equal 4 as well. So there's 3 domain restrictions. X cannot be 2, negative 1, or positive 4. So this domain is slightly different, from negative infinity to negative 1, and then from negative 1 to 2, from 2 to 4, and from 4 to infinity. That's the domain. Okay, open circle f of g So the g function is going inside the f function. The f function is 4 divided by an input, and the input this time is the g function, square root of x plus 2. Now honestly, I'd be okay if you left the function in this form. Technically speaking, you're not supposed to have a square root in the bottom of a fraction, so you're supposed to multiply by the square root of x plus 2 over the square root of x plus 2, and you get 4 square roots of x plus 2 over x plus 2. So there's 2 things to consider. The numerator, because it has a square root, and the denominator. The denominator simply is x cannot be negative 2, but the numerator, x plus 2, has to be greater than or equal to 0, which means that x has to be greater than or equal to negative 2. So now we've got to figure out how to combine these two statements. X has to be greater than or equal to negative 2, but x cannot equal negative 2. So all that needs to be dropped is the equal to part of the inequality. X has to be greater than negative 2. So the domain is from negative 2 to infinity with a parenthesis, not a bracket. And then part B, g of f of x. The f function is going inside the g function, so the g function is a square root of an input plus 2. Now the input is 4 over x. This one's a little trickier. I'm going to combine this into one expression, 4x plus 2. So 4 over x plus 2, I'm going to multiply that by x over x. So 4 over x plus 2x over x is 4 plus 2x over x. So since we're taking the square root of an expression, this expression here, 4 plus 2x over x, has to be greater than or equal to 0. Now, this is called a rational inequality. This is supposed to be part of what's taught in 1010. A quick little review of solving a rational inequality. One of the sides needs to be 0, so that checks out. The right side is 0. Once that's done, you need to find what are called the critical values. The critical values are numbers that make the numerator equal 0 and the denominator equal 0. So critical values, the denominator is going to equal 0 when x equals 0. The numerator is going to equal 0 when x equals negative 2. So those are the critical values. The next step would be to place those on a number line and then choose test values in between each of these intervals. So I'm going to choose a test value of negative 3, a test value of negative 1, and a test value of positive 1. So if I plug the negative 3 into the x's, I'm going to get 4 plus negative 6 over negative 3. So 4 plus negative 6, that's negative 2 over negative 3. A negative divided by a negative. Let me write this down. 4 plus negative 6 is negative 2 over negative 3. A negative divided by a negative is a positive. So this whole region right here, even though the numbers are negative, when I plugged those negative numbers into the original expression, they come out to be positive. So this interval represents a positive interval. Now if I test negative 1 for both x's, negative 1 here and a negative 1 here, 2 times negative 1 is negative 2. 4 plus negative 2 is 2. So I have a 2 on the top. On the bottom I have a negative 1. 2 divided by negative 1 is a negative number. So this is the interval that represents negative, not because these numbers are negative, but because once I plug them into the expression, they come out to be negative. Over here, if I test a test value of 1, 2 times 1 is 2, 2 plus 4 is 6, so I've got 6 over 1, which is a positive number, so that would be a positive region. Greater than or equal to 0. What numbers are greater than or equal to 0? Well, positive numbers are greater than or equal to 0, so we want all the intervals that are represented by plus sign. So we've got this interval, we've got this interval. Now, we've got to be careful about whether to include brackets or parentheses. Greater than or equal to usually means brackets, but I don't want to put a bracket around 0 because I can't divide by 0. I can't have a 0 on the bottom of a fraction, so I'm actually going to put a parenthesis there. So the interval is from negative infinity to negative 2, bracket, parenthesis, union, or union, parenthesis, 0 to infinity. This is the domain. Okay, question 22, find the inverse. First step of finding the inverse of a function or the inverse of a relation here is to switch the place of x and y. So x equals y minus 9 over y minus 2. Next step here is, we don't want to have this fraction, especially if we have a y on the top and a y on the bottom. This fraction is no good, so I'm going to clear out the fraction by multiplying both sides by the denominator. So that's going to leave y minus 2 times x equals y minus 9. I'm going to go ahead and distribute the x and get xy minus 2x equals y minus 9. What I'm trying to do here is isolate y. That's the second step of finding an inverse. First step is to switch the place of x and y. Second step is to isolate y. And the problem is I have a y over here and I have a y over here. I need to get the y terms on the same side of the equation. So I'm going to subtract the y over here and I'm going to move the 2x over here. So I'm going to get x, y, subtract y equals positive 2x minus 9. Now on the left side, both terms have a y as a common factor, so factor it out. And then I want to get, now I have a single y. Here I had two y's, now I've got a single y. But the y is multiplying x minus 1, so I need to divide by x minus 1. And now we have y by itself, so that's the inverse. F inverse is 2x minus 9 over x minus 1. Okay, a quick sketch of this graph. If we move 1 unit to the right and up 3 units, this would be a parabola. Looks something like that. So the domain is all real numbers. The range, the lowest number on the y-axis is 3, so the range is from 3 to infinity. Now, is the function 1 to 1? Remember, the horizontal line test can help you determine that. This graph fails the horizontal line test, so it is not 1 to 1. And that's a problem because part C wants us to find the inverse. In order to ensure that the inverse is a function, we've got to make sure that the original function is 1 to 1. So that's what this second part of part B is asking you to do. Restrict the domain of the function so that it is 1 to 1. Essentially, we're trying to make this graph pass the horizontal line test. So I'm going to imagine this graph with the left half gone. So it starts here and moves up. Now this graph passes the horizontal line test, so it's 1 to 1. The domain restriction now is from 1 to infinity. If I restrict the domain from 1 to infinity, that produces only the right side of this parabola, thus making this function 1 to 1. So now the domain is from 1 to infinity. The range is still from 3 to infinity. Now finding the inverse, if the original function here, the first step to find the inverse is to switch the place of x and y, and then to solve for y. So I'm going to move the 3 over. Don't really need those parentheses. I need the parentheses over here. Now I'm going to get rid of the square by square rooting. Now we have y minus 1 is equal to, now it is true technically that when you take a square root you're supposed to have plus or minus. However, we restricted the domain to make a 1 to 1 function. What that means is when we find the inverse is going to be a function. That's what it means for the original function to be 1 to 1. The inverse is a function. If I have this plus or minus in front of the square root, it's no longer a function. So we can drop the plus or minus. We know that this is going to turn out to be a function because the original function was 1 to 1. Last step is to add the 1s. We have y equals square root of x minus 3 plus 1. This is the inverse. the domain and range, remember the domain represents x and the range represents y. The domain and range of the inverse should be the opposite domain and range of the original function. This was the domain of the original function, this was the range. These represented the x values of the original function, which are now the y values. And then this was the range of the original function, or the y values. So when you find the inverse, those become the x values. Okay, question 24. If we have f of 8 is equal to 1, we're supposed to find that. Well, if I want to get rid of the function f, I can apply the inverse to both sides. The inverse of f and f itself, those are inverse functions, so they cancel each other out. So right here we have f of the inverse of f of 1 is equal to 8. Or another way you could think about this, this is the x value, that's the y value, so we have a point here of 8, 1. They're asking us in the inverse what's going to happen. Well, in the inverse, you switch the place of x and y, so we have the point 1, 8. So if the x value is 1, the y value is going to be 8. Similar argument here. If we have the point 2, -7 in the original function, then in the inverse function we're going to have the point -7, 2. So f of -7, the inverse of f of -7 is equal to 2. Okay, show that the functions are inverse. We have to show that f of g of x is equal to x. We also have to show that g of f of x is equal to x. So the first one here, the f function is 4 minus an input divided by 8. The input is 4 minus 8x. So this becomes 4 minus 4 plus 8x over 8. 4 cancels, so we have 8x over 8. The 8's cancel, and you're just left with x. So that proves the first one. This one here is g of f of x, so the f function goes inside the g function. The g function is 4 minus 8 times an input. The input is 4 minus x over 8. Now if we're multiplying by 8 but also dividing by 8, those are inverse operations. So the 8's cancel first. Now we have 4 minus 4 plus x. It's plus x because the minus sign distributes. And then the x is left over, so that proves the second part.